Okay, let's dive right into this explainer. Think of this as your ultimate highly structured study guide for mastering CSSP Domain 4.0. Look, if you're gearing up for the exam, you already know this domain is an absolute beast. It's packed with overlapping protocols, complex architectural frameworks, and some pretty subtle legal distinctions. But as your instructor, my goal today isn't just to throw facts at you. We are going to build your actual exam mindset. We're going to lock in these core concepts so you can use them as your exact blueprint for success. We're going to attack this massive domain using a strict modular breakdown. We'll start with protocol and authentication security, move into voice and email defense, tackle VPNs and secure tunneling, break down switching and virtual networks, and wrap the whole thing up with NAT and third-party risks. All right, let's jump right into Module 1, Protocol and Authentication Security. This is all about how foundational network communications establish verified identities before a single byte of real data is ever trusted. So, to pass the exam, you absolutely have to be able to rapidly distinguish between these EAP derivatives. Now remember, EAP itself is just a framework, right? It's the implementations that actually secure our environments. Two of the big ones you'll see are PEAP and EAP-TLS, which both give you robust security through TLS tunneling. In fact, EAP-TLS is pretty much the gold standard when both your client and server have digital certificates. Then there's EAP-TTLS. This one is brilliant because it establishes a secure VPN-like tunnel before the authentication process even starts. What does that mean for you? It means your usernames are never exposed in clear text. On the flip side, beware of older methods. LEAP, which was an old Cisco proprietary fix, and EAP-MD5. They are completely obsolete and deprecated. If you see them suggested as a modern security fix on a test question, it's a trap. Do not pick them. Here's a massive CISSP exam mindset note for you, and it's a trap a lot of folks fall into. Do not, I repeat, do not limit 802.1x to just Wi-Fi. Because we're so used to associating it with wireless enterprise networks, candidates totally forget that it actually provides port-based access control for wired switches, firewalls, and VPN gateways too. It's the gatekeeper. It ensures that clients absolutely cannot communicate with a network resource until proper authentication happens. Moving on to Section 2, Voice and Email Defense. What's really interesting here is how we take specific security controls and bolt them onto dedicated communication channels that honestly lack security right out of the box. Time for another exam mindset notes. And look at this one carefully. Assuming voice over IP is end-to-end encrypted by default is a huge pitfall. It's just not. Think about how VoIP works. Gateways have to decrypt and re-encrypt your traffic to connect different service providers or to interface with the old-school public switched telephone network. Because of that, you can't guarantee true end-to-end encryption. Unless you are staying strictly within one single provider's proprietary network, your traffic is literally being decrypted at intermediary gateways along the way. Okay, take a mental screenshot of this one. You've got to memorize these email security protocols because they're your armor against threats. SMIME secures your payload using X.509 digital certificates to give you both confidentiality and authentication. PGP does similar work, but it relies on a decentralized public-private key system and a web of trust. Then you have the DNS level trio, SPF, DTIM, and DMARC. These three operate together to prevent domain spoofing and block business email compromise. Oh, and don't forget Start TLS. That's an explicit command that tells the system to upgrade a plain text SMTP connection right into a secure TLS tunnel. All right, let's transition to Section 3, VPNs and secure tunneling. This is all about establishing secure perimeters across public networks, which is absolutely crucial for today's remote workforces. I love this analogy. Much like a stormy lighthouse cutting through the dark, a dedicated VPN concentrator acts as your secure beacon. It securely guides hundreds or literally thousands of authorized connections through the chaotic, completely untrusted waters of the public internet. It gives you the high availability and the raw processing horsepower needed to handle all of that complex encryption and encapsulation without missing a beat. Now, when the exam tests you on IPsec modes, you have to know exactly where the encryption is happening. In transport mode, IPsec encrypts the payload only. It leaves the original IP header completely intact and exposed. Because of that, you really only use transport mode for host-to-host links inside a network you already trust. Tunnel mode is a different beast entirely. It encrypts the payload and the original header, wrapping the whole shebang in a brand new IPsec header. This is exactly what you use for site-to-site or remote access connections that have to cross untrusted boundaries, like the internet. Similarly, you've got to know the difference between IPsec's core protocols. The absolute key distinction to memorize here is that the authentication header, or AH, provides integrity and non-repudiation, but absolutely zero encryption, none. If you actually need data confidentiality, you have to use the encapsulating security payload, or ESP. Think of ESP as your engine for actual encryption, typically using AES, while also giving you limited authentication and preventing replay attacks. Let's talk about remote users. An exam scenario might ask you how malware managed to sneak into the corporate network from a remote user's laptop. Well, the culprit is almost always a split tunnel configuration. A split tunnel lets a user access your secure corporate VPN and the open wild internet at the exact same time. This creates a really dangerous backdoor that completely bypasses your corporate firewall. A full tunnel, on the other hand, forces every single packet from that client right through the VPN so it can be inspected by your corporate security controls. Full tunnel is the secure choice, for sure. Okay, let's move down to Layer 2 for Section 4, Switching and Virtual Networks, where we'll look at how we manage traffic and vulnerabilities at the switch level. This step-by-step breakdown shows exactly how an attacker can force a perfectly secure switch to suddenly act like a legacy insecure hub. In a MAC flooding attack, the bad guy literally bombards the switch with thousands of spoofed MAC addresses. The switch, trying to do its job, attempts to learn them all, and eventually its content-addressable memory, the CAM table, fills up to maximum capacity. When a switch can't store any more addresses, it fails open. It goes into flooding mode, broadcasting every incoming frame out of every single port. And just like that, the attacker can easily eavesdrop on all your local network traffic. The fix here? Make sure you implement MAC limiting on your switch ports. So, what about keeping our virtual network segments isolated? If you see an exam question talking about isolated VLAN segments being breached but the traffic never actually passed through a router, you need to look for VLAN hopping and double tagging as the mechanism. Here's how it works. The attacker maliciously crafts a frame with two 802.1q tags. The first switch reads and strips off that first tag, then forwards the frame. The receiving switch then reads the second hidden tag and unwittingly drops the payload right into a restricted, unauthorized VLAN. Sneaky, right? When you compare these two switching technologies, the foundational difference really comes down to exclusivity. Remember that circuit switching guarantees a dedicated physical path for the entire duration of the session. Think of those old-school telephone operators plugging wires into a board. Because that path is completely dedicated, the delays are fixed, but if that physical connection drops, boom, the whole session is lost. Packet switching, which is what the modern internet actually runs on, dynamically routes bursty data segments based on logical addressing. It's incredibly resilient to connection loss, but it's much more sensitive to dropped packets and variable delays. Finally, we've arrived at Section 5, NAT and third-party risks. We're going to break down how to mask our internal network architecture and safely manage compliance when connecting with external partners. As a security professional, you must instinctively recognize these RFC 1918 private address ranges. Just memorize them. They are completely non-routable on the public internet. If a public internet router sees a packet with one of these as the source address, it drops it immediately, no exceptions. Therefore, any internal networks using these addresses strictly require NAT, or network address translation, to substitute a public IP address on those outbound packets so they can actually communicate with the outside world. And here is another critical IP range you have to recognize, APPI. APPI assigns an IP in the 169.254 range if a machine simply cannot reach a DHCP server. So here's your exam mindset note on this one. Spotting a 169.254 IP address in any troubleshooting scenario immediately tells you there is a DHCP failure. That machine can only communicate locally with other APPI hosts. Now, in a security context, this isn't always just a broken Ethernet cable. It could actually indicate an active, malicious denial of service attack against your organization's DHCP server. Keep that in mind. Understanding legal and policy thresholds for third-party connectivity is absolutely critical for Domain 4. Let's look at the MOU versus the ISA. An MOU, or Memorandum of Understanding, is really just a formal handshake. It's a document of intent that basically says, hey, our two companies want to work together, but it usually isn't legally binding when it comes to technical controls. The ISA, or Interconnection Security Agreement, on the other hand, is the heavy lifter. That's the strict document that actually enforces the technical security controls, the encryption requirements, and the specific risk management parameters of a direct network link between your infrastructure and a third party. So as you synthesize everything we've covered in this explainer, I want you to ask yourself, How can you leverage these exact concepts to not just pass a certification exam, but to genuinely bulletproof your actual network? From spotting the subtle difference between age and ESP, to stopping a VLAN hopping attack in its tracks, to enforcing an airtight ISA with your vendors, this is exactly how you build a resilient, secure communication architecture in the real world. Keep reviewing these core concepts, internalize this security mindset, and you'll be well on your way to absolutely mastering this domain.